Thank you that we came here. Let's say I'll first introduce myself again. Mostly what I'm doing, I teach people Python, Python internals, bring new contributors to Python, and from education system. Yeah, I built and worked in different companies, built projects, and as hobby I do Python music, but today not about music. Yeah, very good that we have so many events, and especially in Asia, like PythonAsia, where we are now. Thank you, organizers, for that. This presentation created for the two purposes: for report and for have and research deeply after presentation. A lot of links will be in the slides and headers of slides. And if you will have after questions, I will try leave time for your questions. It will be numbers of slides. Okay, let's start. We will talk today about HighLoad Python. We will talk how hardware provide HighLoad, different optimizations, and this is like easy introductions into this is hardware and connection with software. Yeah, how we accelerate our code. From what we will start today, I hope each of you like lunch, but yeah, I also like the lunch. We will start from SIMD. This is SIMD. This is material for producing chips. Yes, if easy explain, easy link. And this is chip execute via registers, via instructions, and optimizations. What we'll discuss today, like simultaneously multi-threading, like SIMD instructions, SIMD registers. And chips can be different, like different architectures, different purpose, GPU, CPU, TPU, and different other more specialized. And this is all execute our code, like print hello world via ecosystem tool like NumPy, Numba, and so on. Okay, how the difficulties come? How much difficult came from SIMD to CPU and use specific models in CPU, create the models via SIMD. It's extremely difficult, and let's talk how it's look like, how we are creating the chips, and how transistors via helicopter view, how it look like, yeah? Because of we want to understand how we will execute fast our code. We should understand via what we will execute our code, via what models, and how the models just approximately constructed. Okay, for the first, we have a wafer. This is called a wafer. This is wafer supplied into manufacturers, like in that containers, manufacturers like TSMC. And the cost $100. It's the ultra clean creamy inodes, slice of inodes. And after that, it will be used as the wafers in different so complicated machines with incredibly parameters of like precision, like temperature, and so on. Very high sophisticated machines. Yeah, and via lithography, we produce different layers of our CPU. Our in general process units. Very difficult process with high temperature in general, very complicated. Yeah, if it will be fast, like visualization, how it's look like that. It's need to be run. Yeah, this is not real speed. It's just very slow-mo. Now we a little bit accelerate. This look like that. This is a wafer with specific material over the wafer silicon, and we produce different layers of our chips. Only one layers of chip. Okay. And we had the wafers. It's costed $100 after 3 months, and around 100 steps, we achieve full wafers, followed by chips like CPUs, GPUs, or other chips. And it's a cost increasingly so much more higher. Yeah, and after that, we cut the wafers and do backend, package our CPU, for example, and supply to our customers. Yeah, it was fast introductions that it was very completely difficult processes with like pipeline, how it's look like. Let's see how it's look like inside. What is inside the CPUs in the almost smallest level. Like what is the transistors? Transistors. These transistors. Do you understand? I think this is very high abstractions. What just give you numbers: 10 nanometers, 7 nanometers, 5, 2, and so on. Okay. Okay. Let's compare with daily objects. What we use each day, and for example. Mitochondria. This is transistor. This is size of transistor. Yeah, for example, 10 nanometers. And this is mitochondria. This is like a power station in almost each cells of our body, what produce specific molecules, call it ATF, and we use it for breathing, for raise our hands, for speech. And this is approximately size. Okay, mitochondria, dust particle, dust everywhere, dust came from each person, and transistors, it seems like nothing comparison with the small dust particle, or human hair. If we'll take your hair and cut it on the slice of the hair, we can place approximately 1 billion transistors. Transistors, it's very, very small objects. Very small objects. What will happen if we will take a bunch of transistors and try create something, some logic? We will achieve logical gates. This is logical gates. This provides some logic, what you easy understand, like AND, OR, XOR, invert, and something more difficult. This is just a bunch of transistors in specific combinations, like micro architecture. These logic gates, this is base for arithmetical units in our CPU physical core. I need my laser, and I don't see my laser. 1 second. Oh, yeah, it's good. Yeah. This is logical gates. It's based for units. This is units. We will come to these units many times, and this is units, call it in general arithmetical logical units, ALU. This do simple arithmetical like summation, multiplication, and so on. And from that units, via one iteration, we reach cores. This is super familiar for you. This is cores. When you do htop commands in your bash, in your shell environment, for example, in Linux, you will see your cores, and about that we will talk a little bit more. And this is cores, is the parts of our CPU. This is what execute with what you communicate via your code. And this is very sophisticated process, came from SIMD to this CPU. It's like very rocket science to produce it is not so easy. It's a super sophisticated, complicated process for what that all people will use for entertainment, for YouTube, TikTok, and so on. or human power focus to produce chip, and people use for shorts. Okay, let's look inside process units. We have different process units, yeah. But in general, all of you, each of us heard about CPU and GPU. They have different purposes. GPU, this is for, it's a few cores. It's a few cores with complex cores, powerful cores, what focus to do fast something complex code with a lot of branches in general purpose and not so much cores. In general, it's 16 cores, around 16 cores for consumer product, but for server, it's like 100, around 100 cores could be. Yeah. And GPU has different architecture. It's a lot of cores, simple cores, focus on simultaneously execution, simple tasks, and with high speed broadcasting data from memory to execution units into process units. Yeah, better if GPU execute the same, many the same independent simple tasks, and it has a lot of threads what help execute. Okay, this is other architecture of NVIDIA. This is one Intel chip. In simple words, it looks like that. CPU, few strong cores, GPU, 1,000 weaker cores. Okay, it was about hardware, about inners of hardware in helicopter view, and let's see how it's connected with software, how we use that when we write Python. When we'll write hello world or something not native Python, but like libraries from our ecosystem, no matter how difficult, how complicated our code, Python code, no matter how it's huge, we display all the complicated logic pure Python, from pure Python code into a small bunch of bytecode. Bytecodes, it's not so many bytecodes. What is around 250, it depends by realization of CPython. And this is middle representation, what link your Python code with C code. Because of Python, this is Python envelope C code, and this is C code executed into your hardware. It depends by hardware how it's executed. Is like RISC or CISC architecture. But in general, this is all bytecode what we receive from Python. Display it into instruction set of your specific hardware architecture. And that's all. This is a very simple helicopter view, how it looks like. It's obviously more complicated. This is how software, our Python, connected via our CPython to hardware, yeah, to hardware. Also, this is plenty not so big. This is also plenty not so big, and you can write whatever complicated code. Okay, how we can use hardware and what hardware, exactly part of hardware you can use to accelerate our code. let's talk about simultaneously multithreading and SIMD, single instruction multiple data. First, I will try explain very fast. To execute logic, what we provide via our code, we need this is code, and we need data to implement the logic. Yeah, the data has different distance from our arithmetical logical unit, from our cores. And this distance we can say like the fastest. This is registers, when data exactly in registers what will be used, or caches. So what is the closest to CPU? Sorry, to cores, or dynamic access DRAM, dynamic rapid access memory, or the biggest distances like SSD and so on. I think many of you saw before this is the result after HTOP. And here is half of physical cores and half of, and all of them is a logical cores. What's the logical cores? We have core, yeah. Inside each physical core, we have logic cores. Logic cores is just, in easy words, is just a pipeline to provide data into our arithmetical logical units about what we had conversation before. And this is arithmetical logical units need data to execute something, need instruction and need data. If we didn't find data in L1 cache, and L2 cache, and L3 cache, if in any caches, or we need to search the data, yeah, and it's mean arithmetical logical units. This is executor parts of our CPU will be stuck, will be waste time. In that time, we can use a second pipeline, logical core, second logical core to provide data into arithmetical logical units. When you use free trading, for example, in Python since 3.13 CPython, or use multi-processing, you work with logical cores. And this is this is named simultaneously multi-threading, or Intel called it hyper-threading. Can provide, can save from 10 to 40 times, 40% compute power. It's mean one logic core miss data, the data start search it into caches, into memory where it's located, and other logic core start supply data. It's called cache miss for one logical core. This is one optimization what we use each day if we work in like multi-threading or multi-processing, and we don't know about the optimization. In general, people who know only Python don't know this optimization. Okay, this is not so difficult optimization in helicopter view, but the most interesting for us, what we can manage, is the next optimization. This I will skip. Yeah, SIMD, single instruction multiple data. For example, we have a bunch of data, and we need to implement the same instruction to each data. For example, we have one vector, other vector, and or no matter, it could be not vector, it could be independent data, but the instruction is the same. We can do first iteration, second iteration, third iteration, and so on. Or we can just store in specific registers our data, implement one instruction, and receive our result. Here, so much less inner process, inner CPU, inner core communication between memory, between asking instruction, asking in the fact instruction. Yeah, we implement here one instruction for all data. Here we implement at least 4 instructions. Let's try to visualize that. Yeah, and call it vector instructions. I think a lot of people heard about vector instructions. This is vector instructions. This is SIMD. We have operator. This is single instruction, single data, and we have other operator, what we'll call single instruction, multiple data. Here we provide one data instruction, also one instruction, and here we provide one data, and here many data. The right side architecture can economy a lot of time. For example, it exists a lot of instructions, different SIMD instructions, and different SIM registers. If we'll talk about XMM, what is this registers? SIMD registers, XMM, one type. The size of physical, this is physical part of your silicon in your CPU. The size is 128-bit. And if you will put inside the size, it's limited size. Data like int8, you can you can locate it 16 int8s, or you can locate it to float 64. And obviously, this will be computed approximately 8 times faster than that data what you located. Yeah, this is like a visualization. This is 2 float 64, and here 16 int8. Yeah. SIMD unit, this is, we can see SIMD unit, and this is located inside power core, and closely located efficiency core, what's called E-core. One SIMD unit has significant size, and obviously size of all chip is limited. We cannot scale it without scaling price of size of chip. Yeah, and it's costly make bigger SIMD instruction. Yeah. Yeah, it's different SIMD instructions what used by different chips. Yeah, how it look like? We have, for example, if we will take instructions AVX2, it will be like 32 cells, and here I wrote a C code. What do sums an array elements into a single accumulator. Yeah, and if we will use int8, it will be so much more faster, almost 8 times faster than int64. When we use int8, we can, in parallel, we can calculate 32 numbers. With int64, we can calculate 4 numbers. It means this is vector instructions what allow us do parallel arithmetics, let's say like that. How we can use it? We are different ecosystem of Python, and we have two. I see 2 ways how to implement it. First, when you have a code base what you don't want change, and in that case you can research Numba. This is a specific framework what can provide different optimizations and SIMD. What's happened? When you wrote your code, for example, this is a simple code, square difference, yeah? You don't want to write the code, you can put decorator over the function and prayer or hope that SIMD will be implemented. How it's work? Numba prepare code for low-level virtual machine, and low-level virtual machine could implement SIMD instructions if SIMD registers and instructions exist in your process, in your CPU, and if it will be reasonable use SIMD instructions over your code. Yeah, and this is just simple benchmark of this code with decorator, without decorator, and this is times what you can see in Google Colab. It's 3,500 times faster with implementing SIMD extractions and maybe some other optimizations via Numba. You just place decorator. A decorator. It's not work everywhere because of can be implemented not everywhere, but here it's work perfectly, and many places in code it's work perfectly. As a simple mathematics, simple example where I implement work with SIMD instructions. Here the code. This is mathematics. First I will do pure Python. This is results. Yeah. I do millions times in cycle. This is mathematics. And after when I will implement Numba or NumPy, what's under hood also use SIMD instructions if it's available in your chip. This SIMD instruction implemented, and we gain a lot of performance. Yeah, if you need to write code from 0 to hero, better use NumPy, obviously, because of its very optimized library. And inside, if it's hardware you allow, NumPy use SIMD instructions. Simple functions realized via NumPy. This is NumPy objects. And NumPy via API can provide access to SIMD extractions. Yeah, and it's very fast. What about GPU? GPU is a different compute unit. Excuse me, how many time do I have? How many time do I have? 4 minutes. Okay, and after that, do we have answered questions? Okay. We have different architecture of GPU, and it's by the architecture allow computate so much faster because of this specific architecture. And if we compare some libraries, if we compare the execution the same code, like high level the same code, like we do this as mathematicals, easy mathematicals on CPU and on GPU. Yeah, via NumPy. And via CuPy, what is like very similar by syntaxes. With NumPy, we reach, it depends by your GPU power and CPU power, but in Google Colab, you can 60 times faster execute this code in GPU. Or this is public benchmarks, chart of the benchmarks, where compare different size of array, CuPy with NumPy, yeah, and difference like fast Fourier transformation, array scaling, SVD, summation, and CuPy, it means GPU, could execute some tasks, some problems so much more faster. Also exist different frameworks, what is more intricate, sophisticated than just CuPy, where you need to create CUDA kernels, where you need to think about how memory bottlenecks and so on. One of that is PyCUDA or CUDA Python also exists, or for different purposes is a Triton. It depends by your tasks or JAX or other frameworks. And this is a logarithmic scale in both sides. Here I compare time execution of NumPy, what's executed on CPU, CuPy, and Numba. Previously, Numba also can execute it in old version on GPU. And I executed this task. Yeah, it's also so much more faster than in CPU. Yeah. That's all. I hope we will have time for the question. This is QR code you can scan and ask me presentation in LinkedIn, or just connect with me and we can meet, hang out in the Philippines and communicate. Thank you for your attention.